Well, good morning. I am Francisco Javier Gañá, and I'm going to present the work named Aerial Manipulation System for Safe Human-Robot Handover in Power Line Maintenance, which is currently being developed in the GRPC Robotics Lab of the University of Seville. First of all, we are going to describe the application scenario and the main contribution made. Next, we are going to visually describe the method, showing all the stages involved in the procedure. And finally, some conclusions and future work. Aerial robots can significantly reduce the time, cost, and risk in the realization of inspection and maintenance of the power grid. In fact, the power grid is a critical infrastructure with a vast extension in any country, where the workers are placed at height and exposed to high voltage. Some of the applications that aerial robots can carry out are the installation of vertiverters on the power lines, or, like the case in this work, helping human workers operate on the power lines. So, the main contribution of the work is the development and experimental validation of a perception system for safe human-robot handover with dual-arm aerial manipulator. On the right, you can see the handover scenario, where the worker is receiving the tool by the dual arm suspended in a long reach configuration. The proposed procedure is illustrated in this state machine. Firstly, in the approach to worker stage, the robot approaches the person until a safety distance, here named SD, is reached. Next, the orientation phase places the robot between the desired angle of relative human-robot yaw angles. The robot remains hovering until the person makes the cam sign, then tracks his hand, and finally hands over the tool. Talking about the hardware, we use an inter-real sense RGBD camera for detection and tracking. Perception methods and control of the arms are implemented on a light computing Raspberry Pi 4. The arms are suspended on a Skytech light multi-rotor. In this first stage, talking about now the stage of the method, YOLO version 5 Nano is used to detect the worker, and his/her 3D position is estimated by combining the RGB image and depth field from the camera. After takeoff, the robot follows an obstacle-free trajectory that uses the worker's location as the goal. It navigates until its distance to the worker is lower than the security distance predefined, here named SD. In the second stage, the orientation, YOLO 5 phase, is used to detect the worker face. Here, the robot defines and performs a circular horizontal trajectory that keeps the robot oriented toward the worker. The circular motion is kept until the relative face camera yaw angle is switchable for handover. As said, YOLO 5 phase is used to detect the worker's face and estimate the relative face camera yaw using the position of the worker nose with respect to the center of the bounding body. In the following states, signs from the worker are recognized to guide the robot. The detection of the hand is made using single shock detector, and the landmarks are estimated using a convolutional neural network. All this is done using MediaPython's Python framework. Gesture recognition is performed using the landmark positions, which are the input of a feed-forward neural network. In a wait, the robot hovers at a security distance while waiting for commands. When the worker makes the sign CAM, the robot moves toward the worker until the distance is lower than a predefined distance, here named HD. During this phase, the hand is detected and its 3D position is estimated using the camera. During the tool handover, the robot keeps hovering. During the tool handover, the robot keeps hovering, and if the worker's hand is recognized as sign open, the manipulator and effector is commanded toward the worker's hand, solving the inverse kinematic. When the worker confirms correct handover with sign OK, the robot returns to the waiting pose. If sign leave is detected, the robots cancel finally the mission. And finally, some conclusions and future work. We are developing a system for safe autonomous human-robot handover at height. We use an anthropomorphic dual-arm manipulator in cable suspended configuration, increasing the feeling of comfort of the worker while receiving the tool. Moreover, this dual-arm manipulator allows the handover of bigger tools and can be employed in tasks of the same application, such as autonomous installation of vertivirtues. The perception techniques are proven to be accurate and successful in the application, but they could be extended, for example, to recognize different tools. Also, a better understanding of the worker's behavior will make the application safer, leading to a more complete procedure design. Thank you a lot for your attention, and follow our latest advances on our social media.
We have that question and answer section at the end of the short presentation. So we'll be moving to the next speaker, William. They will be online as
well. All right, can everyone see my screen and hear my voice?
We can hear you, but the screen which is shared is not, we cannot see the full screen.
You cannot see the full screen? Okay.
Dime. ¿Se ha visto bien?
How about now?
Still we cannot see the full screen.
But on the Zoom side, we can see the full screen. Maybe, is it being truncated for the meeting room?
We can see. Oh, we can see the screen here. Okay, so just give us a second. Yes, we can see the screen now. Yes.
All right. Okay, cool. I'll get started then. Hello, everyone. My name is Ray Chen. I'll present our paper, Task-agnostic Adaptation for Safe Human-Robot Handover. First, let's start with our motivation. In human-robot collaboration, when we apply robotic systems to real-world scenarios, a lot of factors cause the need for case-by-case tuning. In this work, we targeted task-agnostic adaptation as a general framework for adapting HRC systems to various factors. For example, environments, users, and robot platforms. Next, let's see some cases where this is important. For example, the lighting condition in the environment has a great impact on the perception quality. We can see that the perception quality is severely affected in dark environments. The uncertainty of detection can lead to safety issues when human and robot work in proximity. Another example is that different human users tend to interact with the robot in different ways. The user on the left will stand closer to the robot, while the user on the right will stay within a distance and reaches out his hand. This will cause differences in how the robot should deliver the tool, since the robot links are more likely to make contact with the user to the left. The robot platforms can also make a difference. Some robot only takes dense reference trajectories, while others only take sparse high-level trajectories. Robots can also have different dynamic constraints, such as bounded jerk and bounded acceleration. So we need to ensure that the same HRC task can have consistent performance with different robot platforms. Let's now talk about our design of task-agnostic adaptation. To formulate the problem, we first write down the general form of HRC tasks as a constraint optimization problem. The objective here can be any function that is specific to the task. Q here is the robot trajectory and E represents the environment. We split the constraints into two parts, the hardware-related parts, for example, robot kinematics, and safety constraints such as collision avoidance. Now, to address adaptation to different factors, we decompose the constraints into several modules, and each of these modules will handle a certain type of adaptation. So the first module is a function G, which gives the Cartesian goal based on the environment. This function gives us the freedom to adapt to the variations in the environment. The second module is a function F, which solves the joint goal based on Cartesian goal. We can handle the variation of users here. The final module is a safety module, which sits at low level to ensure human safety. We handle the adaptation to robots here since the low-level control often varies from robots to robots. Let's now look into each of these modules and see how they work. First, for the adaptation to environments, we find that with poor lighting, the uncertainty of hand detection also increases. Hence, we treat the detection variance as an indicator of low detection confidence and higher safety risk. We handle this by offsetting the desired end effector precision by amount proportional to the detection standard deviation towards a safe direction. And this safe direction should be designed specific to the task. Note that the detection uncertainty here can also be handled in other manners, such as constraining the robot velocities. In the second module, we want to solve the desired joint goal from the Cartesian goal. This can be done by any inverse kinematics algorithm, but the result joint goal might lead to very small human-robot distance. For example, as shown to the right as the red robot pulse and the blue human pulse. Hence, we adapt to user styles by searching for a better joint goal with a larger human-robot distance, but with the same delivery position. We optimize this by iteratively searching along the known space of the robot Jacobian until we find a local minima of this objective here. We add the orientation error as a regularization term to provide a tunable trade-off between the delivery pulse and human-robot safety. Finally, we handle the adaptation to different robots. We divide the adaptation into two modules, the tracking controller and the safe controller. To adapt the tracking, we view the robot control as a cascade of three levels, the task level, the motion level, and the servo level. If robots operates in different levels, we share the modules outside all the robot control levels and develop robot-specific modules to fill the gap. So in our case, the Fanuc robot operates on motion level, while the Canova robot operates on task level. Hence, we share the task controller and develop a position controller for the Fanuc specifically. To adapt to the safe controller, we adapt the same safe control algorithm, but with different variants depending on the order of the dynamics model. Here we deploy SafeSet algorithm. It defines safety using a function phi and projects the nominal control into the safe set. For the Fanuc robot, we use a jerk-based SSA since Fanuc requires bounded jerk. For Canova robot, we use acceleration-based SSA because its control interface accepts velocity trajectories. Due to time limit, I will omit the details of SSA, and it will be covered by Dr. Changlu Liu in the afternoon talk. Finally, let's see some results on the real-world scenarios in hardware implementation. We first demonstrate a simple task with different lighting. Here, the robot is supposed to deliver the pen to the human's right hand. With poor lighting, the robot delivers the pen with a larger human robot distance. And we can also see that during the motion, the robot keeps a larger distance from the human's body. Now we demonstrate adaptation to users. So in this task, the robot should deliver the power tool to the human. With different users, our framework is able to adjust the desired joint goal to help the robot to avoid unintended contact with humans. This is useful especially in close proximity HRC tasks. We then apply the same human-robot handover task on different robots. We observe consistent tracking performance here, and we plot the robot trajectories to the right. Finally, we verified that the safe controller on both robots. We can see that both robots are able to avoid human in consistent manners and keep the human-robot distance well above the manually assigned safety margin. All right, that will be all. Thank you so much.
So we'll have our last speaker of this short talks. Maria.
Yes. I already am ready here. All right. Okay, so thank you for having me here. I'm Maria Pozzi from the University of Siena, and I'm a postdoc there. And today I want to talk about a type of robot that was born around 10 years ago, as you will see, that are supernumerary robotic limbs, which are robots that you can actually wear, but they are not prostheses that are meant to actually, substitute a limb. They are actually an additional limb to the user body. So supernumerary robotic limbs, as you see here, are defined as wearable robots designed to enhance human capabilities from several points of view. And in this presentation, I will mainly show a few slides about this review paper that we recently published, and which summarizes a bit the state of the art of the field. So we will see some early SRLs, some applications. What are the trade-offs in design, actuation, and sensing for these devices, and some perspectives on the control and feedback interfaces and neuroscientific considerations that are behind the use of supernumerary limbs. So as you can see here, the very first supernumerary limbs started to appear around the beginning of 2010, let's say. But the very first devices, actually working devices, were published in 2014. So in 2012, there was already some initial mechanical design of a device with two supernumerary arms developed at MIT. And then in 2014, different groups, in particular a group, the group led by Professor Azada at MIT and Professor Patrizio at the University of Siena, developed supernumerary fingers as well as supernumerary arms. And then later on, also supernumerary legs were developed. Of course, these are the very first examples, and then several devices have been developed after that. But as you can see, this summarizes also the type of device that we can find. So there are fingers or multiple fingers running up to hands. There are some works that are about adding a third hand to the human body, and then supernumerary arms and supernumerary legs. So these are the types of limbs that you can find in the literature. And even if this section is actually the last section in our paper, I wanted to start with the applications because, those are the motivation behind the use of supernumerary limbs. So an additional limb can actually augment the human capabilities in healthy people, and so can support workers, for example, in tedious or works that are difficult to do with just two hands. So here you can see an example for welding a component. You might need a third arm. Actually, there are not so many actions that require 3 arms, because our world is designed for 2 arms, right? But there are some of them, and if we think about them, we'll find other applications, I think. And then there you can see a worker actually using a 3rd arm for fruit picking, for example. And there are other works that are more about using supernumerary arms in difficult environments, or to help to hold large pieces where a human can work on. An example was here for this image, where the device, the 2 arms are used to hold a part of an airplane. But one of the most promising applications, I would say, is that in of using supernumerary arms and fingers in assistive scenarios. So here you see, for example, a relatively simple device, because it's a single finger applied to a pharetic hand of a stroke patient. So here, of course, I mean, the stroke patient still has an arm, so you cannot really use a prosthesis, of course. But the arm has lost its function of grasping, so the hand has lost its function of grasping. The arm might or might not be fully pharetic, it depends on the situation. But here, the additional finger allows to regain the grasping capability. So it's recreating a simple grasp. Sorry, I just forgot to take my mask away. So, and assistive applications are now being developed more and more. And as you can imagine, adding a simple finger like that instead of adding a wearable arm, it's much easier, above all if you're talking about patients with motor disabilities. So that's why I'm showing arms in the augmentation side and fingers more on the patient side, but of course there are both ways. And so let me go a bit deeper into the trade-offs in terms of design that you can have to face when you have to design this kind of robots. Of course, if you want to have wearable devices, you have to trade that wearability for dexterity. You might not have so many degrees of freedom on the arm, because the more motors you put there, the more weight you have, and then the payload might be limited, and also the power is limited if you want to wear the device. Please let me know if I'm late. Yeah. And the trend here is to go towards soft robots, which is something that's happening also in other fields of robotics. And the idea now is because if you have a rigid device, you have to control all its degrees of freedom in order not to hurt the person that is wearing the robot. But instead, in soft robotics, if you have a soft structure, then you can actually control the robot for performance, while the safety is provided by the compliance of the structure. And then here you can see another important part of the system is the interface between the robot and the user. And we can have different interfaces, and some of them also provide some feedback to the user. So the idea is that the interface should control the motion of the robot and give feedback on what happened on the robot side to the human. But still, at least for arms, supernumerary arms, the idea of giving additional feedback to the user, like acknowledgements or tactile feedback, it's less exploited. So our perspective is probably it's just to put this wearable word into brackets, between brackets, because a supernumerary arms might not even just a supernumerary limb might also be not wearable, but still connected to the human body through sensory motor interface. So our idea is to replace the physical connection that supernumerary limb that is worn on the user is giving through sensory motor interfaces. And of course, this opens up several questions from the neuroscientific point of view, and also when applied to patients from clinical point of view. So, I mean, thank you for your attention, and if you have questions, I can answer now. Sorry.
We can take questions for all the three speakers. Any questions?
So my question is for Francisco. So when you're running your system, like from the beginning to the end, like how much failure would occur every time you were trying to reproduce the handover? And what was the weakest part of it? Which one would fail?
Sorry, can you repeat the question? I cannot hear it well.
Can you speak louder?
You can talk here, like I can just unmute.
Yeah.
Yeah, I can. I think this is a microphone too. So when you're trying to run your system from the beginning to the end for the handover task, is it reproducible or do failures occur? And if so, what was the weakest part of the state machine or part of the state machine?
Okay. The system has proven to be successful in 20 experiments that we conduct indoors in the test bed. Well, there are some errors in the detection of, for example, the person and the hand, but because sometimes the image is like because of the pendulum, the image is not clearly seen by the robot. But these errors are compensated because to go to another stage of the procedure, we have set the need to be 5 or a parametricized times that the detection has to be made. So there is not only a unique detection to change the stage, but maybe 5 consecutive detections to go to another stage, or 2 or 3.
Okay, thank you.
I had a question. So do you have any experience with like weight or like balance or mobility with these extra limbs or assisted limbs?
So I'm not completely sure about, so there exists some superior limbs, like actually configured as kind of legs that are actually for balancing the first posture of people, but also, for example, arms that help to balance while you're, working on a piece of.
So if you're if you're using one, like if you have or using like an additional arm, is it hard? Have users found it difficult to like maintain balance?
Yeah, I mean, there are some studies, but still there are not so many, user studies yet. So yes, of course, balancing is a problem, and also there are studies on the inherent feedback that you get when you are wearing an arm. So how to actually exploit that inherent feedback that arm is giving you to know something about the arm, for example. So yeah, I mean, balancing is indeed a problem, and it's being studied. Yeah. Results are, I would say, it depends on the device. So it really depends on the single paper developing the single device. Thanks.
I have a question for Rui. Rui, can you hear me?
Yes, yes.
So a question is, do you assume prior knowledge about the lighting condition when you're making the adaptation, like well lit or not very well lit?
We don't have assumption on the actual intensity of illumination of the environment. We do monitor the trend of the changing of the light and adjust our handover pulse accordingly.
Right. So like when in low lighting conditions, you will have poor performance from the open pulse, right? So how do you know what is poor performance? Like, do you have any threshold?
Ah, I see. So we view the perception as a stochastic process. So we just sample detection results from different time steps and for a little while and calculate the statistics from it.
All right. Thank you so much for the answer.
No problem.